Okay, so part 2 of Plasma Physics 2 practice exam. Let's go to number 7. The collisional uh, evolution of the distribution function may be modeled using the FP equation. Write the general form of FP equation for Coulomb collisions. So for this, a general FP collision operator may be written as the following. Okay, so this partial dv dt sub c equals negative partial d dv sub I times quantity a sub I v of f plus 1/2 that's d squared over d v sub I d v sub j times the quantity d sub I j v of f. Okay, so and technically this is second partial with respect to v. Pardon me if I misspoke anywhere. So second partial with respect to d to v sub I, v sub j. Now from here, a sub I, that is the drag coefficient, and d sub ij is the velocity space diffusion tensor. Okay, so two important quantities, very important equation. Part B, explain the physical meaning of dynamical friction and velocity space diffusion. So this is more of a textbook answer. Dynamical friction slows particles systematically due to cumulative Coulomb interactions. Velocity space diffusion represents random spreading of particle velocities due to many small deflections. So that's canonical. Part C, show why Coulomb collisions are dominated by small angle deflections. Okay, so moving along here. Okay. So, what we could say here, the Coulomb force is long range, so large impact parameter collisions are common. Each produces only a small angular deflection, but many such deflections accumulate. Therefore, Coulomb collisions are dominated by small angle scattering rather than rare large angle scattering. Okay. Part D, just saying what they wanted. Define the Coulomb logarithm and explain its origin. So this is textbook canonical as well. So the Coulomb logarithm is, we have ln lambda equals ln of b sub max over b sub min. And usually b sub max approximates lambda sub d. And b sub min is set by either the distance of closest approach or quantum diffraction. It arises because the Coulomb collision integral has logarithmic sensitivity to impact parameter. All right, and letter E, what they wanted, estimate the electron collision frequency scaling with temperature and density. Okay, so the electron collision frequency scales is this. So V sub E sub I, I'm sorry, that's nu. I always do this, especially if I'm reading fast. I always wind up reading things in terms of English alphabet instead of Greek alphabet. My apologies. Mine skips. User error. So we have nu sub E sub I proportional to n sub E log lambda over t sub E 3 to the 3/2. So that's the electron collision frequency that scales as that. So collisions become weaker at higher temperatures and stronger at high density. Okay, from that formula. Okay, interesting. All this stuff is interesting. Moving forward, that's 7, A, B, C, D, and E. We can move to number 8. Okay, number 8. So let's see, magnetized plasma. So number 8, consider. So this drift waves problem. Consider a magnetized plasma with density gradient in the x direction and magnetic field. This B, magnetic field equals BZ hat. Part A, derive the electron diagmatic drift velocity. My apologies for the crossing out. So this is drift waves problem. Part A, The diamagnetic drift is this: V sub star E equals negative del P sub E cross B over E sub NE B squared. And for our magnetic field, that's equal to B Z hat. And del P sub E equals D P sub E dx x hat. So V sub star E equals negative 1 over E N B squared. D P sub E dx times the quantity, cross product x hat and B Z hat. Now, since we have this nice relationship here, the cross product of x hat and z hat equals negative y hat, we could do the following in relation to this. V sub star E equals 1 over E and B, D P sub E of dx y hat. And for isothermal reactions, P sub E equals N T sub E. So V sub star E equals negative T sub E over EB. And then we have D, ln, and naught over dx. So the derivative d dx, ln, and naught y hat. Okay, so that takes care of letter A, deriving the electron diagnetic drift velocity right here. Letter B, show that the drift wave frequency is approximately W sub star equals negative K sub Y T sub E over EB. And then we have the D, ddx ln n sub n naught. Okay, so right here, the drift wave frequency is approximately W sub star equals Ky V sub star Ey. Using sign conventions for electron charge, we could write it as the following. And I said W. I'm sorry, that's omega. My apologies, omega. I do this all the time. My apologies. Omega sub star equals negative K sub Y T sub E over EB. Times we have the D dx ln of n naught. Okay, so that is drift wave frequency approximation. That's for B, so A and B. Now we can move along to C. So C, we want to explain physically why drift waves can become unstable in the presence of finite resistivity or kinetic effects. So let's see here what we could do for C. Oops. Okay, so for letter C, we could say that drift waves become unstable when density perturbations and electrostatic potential perturbations are out of phase. Resistivity, finite and Larmor radius effects, trapped particles and kinetic resonances can produce the required phase shift. Okay, so that's letter C. Letter D, I'm going to read off this. And these are canonical, C, D, and E. Discuss anomalous transport caused by drift wave turbulence. Okay, so drift wave turbulence produces E cross B transport. Fluctuating potential causes V sub E equal the cross product of the electric field and magnetic field over B squared. Correlations between density fluctuations and radial E cross B velocity produce particle and heat fluxes. Okay, so that's part D. And part E, they want us to compare classical, neoclassical, and turbulent transport mechanisms in toroidal plasmas. Okay, so letter E. Classical transport comes from ordinary collisional diffusion across magnetic fields. Neoclassical transport includes toroidal effects, trapped particles, banana orbits, and magnetic geometry. Turbulent transport comes from collective fluctuations and is often much larger than classical or neoclassical transport. So that takes care of number 8. Okay, moving along, and now number 9. Okay. And number 9, I apologize for the crossing out. Number 9, kinetic transport in magnetized plasmas. So, number 9, kinetic transport in magnetized plasmas. So for letter A, define the guiding center approximation and list the conditions under which it is valid. Okay, so kinetic transport, and this is canonical. The guiding center approximation averages over fast cyclotron motion. It is valid when we have this piece of L is less than or equal to, oh, actually, wait a minute, rho. My apologies. Okay, rho sub L is much less than L, and pardon my horribly drawn omegas. Omega sub C is much greater than lowercase omega, where rho sub L is the gyro radius, L is the equilibrium scale length, and omega sub C is the cyclotron frequency. Okay. Alrighty. So B, the grad B drift. Express the grad B drift velocity for ions, and also for C, expressing the curvature drift velocity. This is canonical. The grad B drift is V sub del B equals U over Q, and then that's B cross magnetic field cross del B over B squared, where mu equals mv perpendicular squared over 2b. And equivalently, we could say for this, V sub del B equals mv perpendicular squared over 2qb cubed times the magnetic field, and that's going to be crossed with del B. Okay. And from here, let's see here for curvature drift. All right. Express the curvature drift velocity. Curvature drift is V sub C equals mv squared parallel. Okay, so mv parallel squared rather. So over qb, and then we have times b, and then that's going to be crossed with our kappa, and where B equals magnetic field of B over B, and kappa is B dot del B. Part D, explain why trapped particles arise in toroidal geometry. So in toroidal geometry, B is stronger on the inboard side and weaker on the outboard side. Conservation of magnetic moment, mu equals mv perpendicular squared over 2b, happens to mean the particles moving into the stronger B convert parallel energy into perpendicular energy. If V sub parallel reaches 0, the particle reflects and becomes trapped. All right. Part E, discuss the role of trapped particles in neoclassical transport. Trapped particles execute banana orbits. These orbits enhance radial transport beyond classical predictions. Trapped particle effects are central to neoclassical viscosity, bootstrap current, and trapped electron drift instabilities. So that takes care of A through E for number 9. And now we could go to number 10. Okay, so number 10, let's see. Okay, 10. A lot of 10 is canonical, especially C, D, and E. C, D, and E are canonical. So synthesis problem. Okay, for number 10, a tokamak plasma has the following properties. B sub 0, B naught is 5T, R naught 3.5 M, A 1.0 M, N equals 8 times 10 to the 19th M negative 3, T sub B equals T sub I equals 8 keV. Part A, estimate the electron's thermal speed. So here's part A. Electron thermal speed may be estimated using V sub THE equals square root 2T sub E over M sub E. And we're using the square root of 2 convention. We're going to convert T sub E equal to 8 keV equals 8 times 10 cubed times 1.60 times 10 to the negative 19 joules. So T sub E is going to be 1.28 times 10 to the negative 15 J. Then from there, just using our formula, V sub THE equals square root of 2 times 1.28 times 10 to the negative 15 over 9.11 times 10 to the negative 31. So our V sub THE thermal speed, electron's thermal speed, is approximately 5.3 times 10 to the 7th meters per second. Moving along to letter B, estimate the ion gyro radius assuming deuterium ions. Okay, so for deuterium, M sub I approximates to M sub P. That equals 3.34 times 10 to the negative 27 kilograms. The ion thermal speed is V sub THI equals square root 2T sub I over M sub I. And that's going to equal V sub THI is approximately 8.75 times 10 to the 5th meters per second. So the ion cyclone frequency right here, that's going to be, pardon me for that, omega sub I equals EB over M sub I. Okay. All right, so that takes care of A and B. Now, letter C, they want us to discuss whether a fluid or kinetic description is more appropriate for 1, global equilibrium, 2, Landau damping, 3, drift wave turbulence, 4, tearing modes. So C, D, and E are canonical, and we can refer back to D and E of this page when we get to them. So okay, so here we go for C, for part 1 here. Global equilibrium. Fluid MHD is usually appropriate because equilibrium depends on macroscopic force balance. Okay, and this is canonical. 2, Landau damping. Kinetic theory is required because resonant particles dominate the physics. Part 3, drift wave turbulence, kinetic or gyrokinetic theory is often required, especially for collisionless or weakly collisional plasmas. And part 4 here, resistive MHD can describe basic tearing physics, but kinetic effects may be needed for collisionless tearing or small-scale reconnection layers. So that's for letter C. Referring to the prompt, let's see, for letter D, they say for letter D here, suppose the pressure gradient is increased significantly. Discuss which instabilities are likely to become more dangerous and why. Okay, and sorry for the crossing out. So for letter D here, increasing the pressure gradient makes pressure-driven modes more dangerous. Ballooning modes become more unstable because alpha is proportional to negative dPdr. Drift instabilities also become stronger because the diamagnetic frequency depends on the density or pressure gradient. Tearing modes may also be affected if pressure gradients modify current profiles or bootstrap current. So that's for letter D, canonical. Letter E is canonical as well. Letter E, explain qualitatively how magnetic shear, shaping, and kinetic effects interact in determining confinement quality. So here we go. Magnetic shear can stabilize or modify instabilities by distorting perturbations across flux surfaces. Okay. Shaping can improve stability by altering curvature and increasing stable operating limits. Kinetic effects determine resonant wave particle interactions, trapped particle transport, and collisionless damping. Good confinement requires balancing all three: favorable equilibrium, stable pressure gradients, and controlled micro turbulence. Okay, and that's all for part 2, and that's the full practice exam. 10 problems. Hopefully this could help you prepare getting ready for exam, and thank you for watching. Have a great day.